Cosmic Enigma, the universe's accelerating mystery. The universe's shocking secret. What if the universe's ultimate fate isn't what we've always imagined? What if an unseen cosmic force is silently, relentlessly pushing the very fabric of space apart, faster and faster with every passing moment? For millennia, humanity has gazed at the night sky and pondered its place in the vast cosmos. Based on our understanding of gravity, scientists had long predicted that the universe's expansion must be slowing down. The gravitational pull from countless galaxies and matter strewn throughout the cosmos was expected to draw everything back, causing the expansion to gradually decelerate. But in 1998, a groundbreaking discovery completely upended this expectation. Our universe isn't just expanding, it's accelerating. This revelation was a total shock to astronomers, forcing a fundamental re-evaluation of our cosmic models. This finding was not merely an incremental addition to existing knowledge. It represented a paradigm shift, overturning long-held scientific assumptions about the universe's dynamics. The accelerating expansion of the universe indicates a mysterious unseen force driving it, an unseen hand shaping the universe's destiny. In this video, we will delve into how this astonishing acceleration was discovered, explore the mysterious force driving it, and ponder the profound implications for the universe's distant future. A cosmic revelation, from expansion to acceleration. To truly appreciate the surprise of this discovery, we must first understand the historical context. For centuries, and even into the early 20th century, the prevailing scientific view was that the universe was static and unchanging. This belief was so strong that even Albert Einstein, when formulating his groundbreaking theory of general relativity in 1917, added an arbitrary term to his equations, the cosmological constant, specifically to counteract gravity and keep his theoretical universe from expanding or contracting. Then came Edwin Hubble's monumental observations in 1929. By studying distant galaxies, he made a revolutionary discovery. They weren't static. They were all moving away from us. And the farther away they were, the faster they appeared to recede. This was the irrefutable evidence of an expanding universe. Upon learning of Hubble's findings, Einstein famously discarded his cosmological constant, reportedly calling it his greatest blunder, as it seemed entirely unnecessary in an expanding cosmos. For the next several decades, the scientific community largely believed that the universe, dominated by matter, would inevitably experience a gravitational slowdown in its expansion. The key question was whether this deceleration would lead to a big crunch, where the universe eventually recollapses, or if it would simply expand forever, but at an ever-decreasing rate. However, the universe, as it often does, had another surprise in store. The 1998 discovery of accelerating expansion meant that Einstein's greatest blunder was suddenly back in the spotlight, not as a static force, but as a repulsive one, pushing the universe apart. The cosmological constant was introduced by Einstein, then abandoned, and then unexpectedly found renewed relevance with the discovery of accelerating expansion. This illustrates the nonlinear, iterative nature of scientific progress, where even seemingly wrong ideas can contain elements of truth that become apparent only with later discoveries. The cosmic yardsticks, unveiling acceleration with supernovae. So how did astronomers manage to measure something as grand as the universe's acceleration? They used a crucial tool: standard candles. Imagine trying to figure out how far away a light bulb is in a vast, dark room. If you know the light bulb's true brightness, its wattage, you can determine its distance by how dim it appears. In cosmology, standard candles are cosmic objects with a known intrinsic luminosity, allowing astronomers to calculate their immense distances. The most reliable of these cosmic yardsticks are Type 1a supernova. These aren't just any exploding stars. They originate from a white dwarf star in a binary system that siphons off matter from a companion. When the white dwarf accumulates enough mass, reaching a critical threshold, it undergoes a catastrophic thermonuclear explosion. The key is that because they all explode at this precise mass, Type 1a supernova have an incredibly consistent peak brightness. This makes them exceptionally reliable standard candles, like cosmic light bulbs of a perfectly known wattage, visible billions of light years away. In the mid-1990s, two independent research teams embarked on a mission to measure the universe's deceleration rate using these supernovae. The Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, co-led by Brian Schmidt and Adam Rees, meticulously observed distant Type 1a supernova. The shocking outcome: the distant supernovae appeared fainter than expected. If the universe were decelerating as predicted, these distant objects should have appeared brighter. This unexpected faintness meant the supernovae were further away than predicted, implying that the universe had expanded more than anticipated since their light began its journey. The Hubble diagram for Type Ia supernova, a visual plot of the relationship between redshift and apparent brightness, showed that the observed points all lie above the line for a universe with zero cosmological constant, favoring a positive cosmological constant. This emphasizes that observations of distant objects are not just snapshots of the present, but are effectively looking back in time. The groundbreaking conclusion, announced in early 1998, was undeniable. The universe's expansion is accelerating. This counterintuitive, revolutionary finding earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. Dark energy, the universe's mysterious engine. The discovery of accelerating expansion immediately raised a profound question. What force could possibly be driving this cosmic acceleration, overcoming the universe's own gravity? Cosmologist Michael Turner coined the term dark energy to describe this mysterious, unseen force. It's a catch-all term because fundamentally, no one has ever directly seen or measured it. We call it dark, not because it absorbs light like dark matter, but because it remains elusive and unknown to us. It's an unidentified dark force that controls universal expansion. To visualize this expansion, imagine dots representing galaxies on the surface of a balloon. As the balloon inflates, the dots move farther apart, but the dots themselves aren't moving through the surface. The surface between them is expanding. Similarly, think of raisins in rising bread dough. The universe expands into itself, not into some external void. Dark energy is the force inflating this cosmic balloon, making the space between galaxies grow faster and faster. This mysterious dark energy acts as a repulsive force that pushes galaxies apart, directly opposing gravity. To achieve this acceleration, it must possess a strong negative pressure. Perhaps the most astonishing fact about dark energy is its sheer dominance. Current estimates suggest that dark energy constitutes a staggering 68% of the total energy content of the universe, dwarfing the combined percentages of dark matter and ordinary matter. This reveals a profound gap in our fundamental understanding of the universe's composition and evolution. While its true nature remains unknown, scientists have proposed leading theoretical explanations. The cosmological constant, lambda. This is the simplest explanation, suggesting dark energy is an intrinsic, fundamental energy of empty space, often called vacuum energy. The key idea is that this energy is a property of space itself and would not be diluted as space expands. As more space comes into existence, more of this energy would appear, naturally causing accelerated expansion. However, a major outstanding problem is that quantum field theories predict a cosmological constant that is about 120 orders of magnitude too large compared to observations. This massive discrepancy is one of the biggest puzzles in physics. Quintessence. This is a more dynamic theory proposing dark energy is the potential energy of a dynamical field that can vary in space and time. Unlike the constant nature of vacuum energy, quintessence could fluctuate, potentially offering a different evolutionary path for the universe. The universe's destiny, a future accelerated. The accelerating expansion of the universe has profound and, frankly, chilling implications for its ultimate fate. For decades, the debate among cosmologists centered on two main scenarios: a big crunch, where gravity would eventually halt expansion and pull everything back into a singularity, or an ever-slowing expansion, where the universe would expand forever but at a decreasing rate. However, with the discovery of dark energy's dominance, current observations strongly suggest that the universe will continue expanding forever. This leads to two primary, albeit bleak scenarios for the cosmic future. Heat death, also known as the Big Freeze or Big Chill. This is currently the most widely accepted theory for the universe's ultimate fate. As the universe expands indefinitely, it will become increasingly dilute, cold, and empty. Over unimaginable timescales, existing stars will exhaust their fuel and fade away, leaving the cosmos in perpetual darkness. Even the most massive black holes will eventually evaporate into fundamental particles. Ultimately, the universe will reach a state of thermodynamic equilibrium, a uniform, extremely low temperature, where all energy is evenly distributed and no energy differences exist to perform work. This means no processes can occur, leading to a universal rest and death. The Big Rip, a more dramatic and speculative hypothesis. This scenario arises if dark energy's repulsive force increases over time, rather than remaining constant. In this terrifying vision, dark energy would eventually become so overwhelmingly powerful that it would overcome all other fundamental forces in the universe. Gravity, the electromagnetic force, and even the strong nuclear force. This would lead to a progressive tearing apart of all structures. Galaxy clusters, individual galaxies, stars and planets, and finally, even atoms themselves would be torn into their constituent elementary particles. The universe would end as a singularity of infinite energy density and expansion rate. The universe's fate depends on the ongoing cosmic tug-of-war between gravity, which pulls things together, causing deceleration, and dark energy, which pushes things apart, causing acceleration. The ultimate outcome hinges on how the strength of dark energy evolves over time. The ongoing quest, probing the dark. Despite the groundbreaking discovery, the accelerating expansion and the nature of dark energy remain one of the biggest, most exciting mysteries in modern astrophysics. Scientists are relentlessly working to unravel its true identity and implications. This quest involves a global effort, leveraging cutting-edge technology and international collaboration through various space missions. Hubble Space Telescope. For over 30 years, Hubble has been a cornerstone in measuring the universe's expansion rate. James Webb Space Telescope, JWST. As Hubble's successor, JWST is now tag-teaming with Hubble to produce even more definitive measurements, helping to confirm Hubble's accuracy. ESA's Euclid mission with NASA contributions. Launched in July 2023, Euclid aims to map billions of galaxies in 3D across a vast cosmic volume to understand how dark energy's influence has changed over cosmic history. NASA's Nancy Grace Roman Space Telescope, set to launch by 2027, this mission will conduct wide celestial surveys specifically designed to study the influence of dark energy, complementing Euclid's observations and further refining our understanding. One of the most pressing current puzzles in cosmology is the Hubble tension or Hubble constant puzzle. This refers to a significant discrepancy. The universe's current expansion rate is consistently faster than what's predicted, based on observations of the universe's initial conditions and our current standard model of cosmic evolution. This tension strongly suggests that something else, not measurement errors, is influencing the expansion rate, potentially hinting at new physics beyond our current understanding. Ultimately, breaking the dark energy mystery will transform our understanding of cosmological destiny and cosmic dynamics, opening new chapters in our cosmic story. Conclusion: the enduring enigma. we have taken an incredible journey from the initial shocking discovery that our universe is not slowing down but accelerating to the profound mystery of the dark energy, this cosmic engine. The key takeaways remain. The universe is expanding faster, propelled by an unknown force, leading to potential, vastly different futures like the cold, dark heat death or the dramatic Big Rip. The entire story of accelerating expansion, from the initial static universe through Hubble's expansion to Einstein's blunder becoming relevant again, and finally to the current Hubble tension, demonstrates that scientific understanding is a continuous process of refinement and reevaluation. Science is an evolving narrative where surprising, unexpected results are not failures, but opportunities for deeper understanding. The two biggest unresolved issues related to dark energy, the vacuum energy catastrophe, the 120 orders of magnitude discrepancy for the cosmological constant, and the Hubble tension, both point to fundamental inconsistencies or gaps in our current theoretical frameworks. They suggest that our understanding of gravity and quantum mechanics might be incomplete or incompatible. This cosmic enigma, far from being a sign of scientific failure, is a testament to the vastness of what we still don't know and the thrilling frontier of discovery that lies ahead. It's a reminder that the universe is far more complex and surprising than we could have ever imagined. The universe continues to surprise us, challenging our assumptions and pushing the boundaries of human knowledge. The accelerating expansion is a profound reminder that the cosmos holds secrets far grander than we can imagine, waiting for us to uncover them, one cosmic enigma at a time.